Electric potential. This is a standard end of chapter problem, and it's pretty straightforward. I've drawn my picture, put in Q1 at the origin and Q2 up on the y-axis there, Q3 on the x-axis, and we're going to move Q3 from where it is up to the other corner of this square, to AA. And if you remember your electric fields, which you should, it was just last chapter, those are conservative fields, just like a gravitational field. And when you move and that field does work, it's a conservative force, and so the work done is independent of the path taken. So we could take a path straight from Q3 up sort of parallel to the y-axis here, or we could take any other path to figure out the work done. And when you see work, if you're like me, you're thinking sort of force times distance. You're thinking maybe this formula. Force times distance only works if the force is constant, right? And it's in the same direction as the distance. But our more general formula was the integral of F dot dr. So it's a dot product. The force and the displacement gives us a dot product. And you have to integrate it just in case the force isn't constant to find the work done. And in this case, if you try to do the whole thing at one time, it's pretty tricky. The forces are pointing in different directions. That would be a pretty tough integral. Now, if you really wanted to do this approach, you could break it up into two problems. You ignore Q2, pretend Q2 is not in the situation at all, and you find the work done by Q1 in moving Q3 from its starting point to its ending point. And you can find a path to take that would be fairly easy. You'd have to break it up into a path that's in the same direction as the electric field lines, and then one that's perpendicular to that. And that would be fairly easy to do, to find the work done by Q1 in moving Q3. And then you ignore Q1. You say, you pretend Q1 is not in the situation, and you find the work done by Q2 in moving Q3. And then you add them together. You can do that. Actually, it might be good practice for you to do that. But I'm going to do it differently. I'm going to use electric potential. So this looks like it would be too hard to do. And this, this is a fairly simple situation with 2 point charges. If I gave you a little more complex situation, you wouldn't even consider using this. You'd go right to electric potential. All right, so we know that another way we can find work done is it's the change, usually negative, delta U, right, where U is our potential energy. And this is why we define potential energy. Anytime we have a conservative field, the first conservative force and conservative field that we got was gravitational field and the gravitational force. And so we came up with a potential energy and said work is change in negative change in potential energy. The second conservative force we came across was a spring force, and we defined a potential energy for that. Said work was negative delta U. And then we've got the electric force was conservative, and we're saying work is negative delta U for our electric forces. And delta U is Q delta V. Where V is our electric potential. So some books will write work is equal to minus Q delta V, and some books will write work is equal to Q delta V. And if you're the type of person who just likes to sort of memorize equations, you're going to get messed up here. It depends on what we're talking about. Depends if we're talking about the work done by an external force or the work done by the field. Okay, so what I like to do is forget about the negative signs and then think about it at the end and figure out whether this is a positive work done by the field or negative work done by the field or positive work done by an external force or negative work done by an external force. Let's think about it at the end and make sure it makes sense. And I'll go over a couple of different ways to do that. Okay, so let's find first the magnitude of the work done. And what I'm going to need here is delta V. So delta is always final minus initial. And my V final is going to be due to 2 point charges. Q1 and Q2 are both creating a potential at the starting point, and they're both creating a potential at the ending point, and we ignore Q3 for now. We're going to stick Q3 into those 2 points and see how its energy changes. But we need the potential due to all the other charges without Q3. So the potential at the ending point is going to be the potential due to Q1 at the ending point, at the final point, plus the potential due to Q2 at the final point. And these are point charges, so for potential we can use KQ, and the charge is Q1, over R1 final, plus KQ2 over R2 final. So let me go back and just point to these real quickly on my diagram. So the final location is here at AA, and the distance from Q1 I will call R1 final, and the distance from Q2 I will call R2 final. So you can see that one of them, the distance from Q1, is just the hypotenuse of this triangle, or the diagonal of the square, if you want to think of it that way. And the distance from Q2 is just the side of the square. Okay, so I'll punch those numbers in here. I've got K. Q1 is 4 times 10 to the negative 6th coulombs. The distance is 2 times the square root of 2 meters. My other charge is negative 2 times 10 to the minus 6, and its distance is 2 meters. And when I punch the numbers in, 3.72 times 10 to the third volts. I got 3.72 kilovolts for my voltage at my final position. Now we want to go back and do the initial position. And the initial position is also going to have a contribution from each of those 2 point charges. So it's going to be the potential from Q1 at the initial position plus the potential from Q2 at the initial position. KQ1 over R1 initial, KQ2 over R2 initial. And what do we have? We've got 4 times 10 to the minus 6 as our charge, and we have 2 meters as our distance, and the other charge is negative 2 times 10 to the minus 6, and it's 2 times the square root of 2. So I get 11.62 times 10 cubed volts, so 11.6 kilovolts. Now we want to take our difference between these two, delta V, V final minus V initial. And I always like to think about this for a minute. Are we going from high potential to low potential, or low potential to high potential? We're starting out at 11.6 kilovolts and ending up at 3.7 kilovolts. So we're going from high potential to low potential. We're going down the potential hill, as I like to think about it. And that's important when you're trying to figure out the work done, the sign of the work done. So I do the subtraction. I get negative 7.90 times 10 to the third volts, or another way of writing that, negative 7.9 kilovolts.